Hello, and welcome back to the final speed run of day 4 of the IB speedrun with me, Vince. We're going to be going over the chapter 1 review, and we're going to be answering some questions in there just to make sure you know that we've got everything in this chapter and that we've learned everything we need to know. So let's jump right in. So, as usual, we're going to be doing every other question, and I think I'll start with question 2 this time. Gonna mix it up always. So today we'll start with the even, or not today, but the speedrun will start with the even questions, and question 2 happens to be find the sum of the series 1 plus 2 plus 3 plus 4. So find the sum of all of the numbers until 64. And so this is sum of an arithmetic series. If you don't remember what it is, first term will be 1, last term will be 64. So there are 64 terms in total. So the answer will be 64 divided by 2 times first term plus last term, 1 plus 64. In other words, 64 times 65 divided by 2, which is 32 times 65, which is equal to 32 times 65 is equal to 2080. So that is the first problem down already. Pretty fast if you ask me. So yeah, got it correct. Now let's move on to the next one. So the next problem is problem number 4, which we need to prove the identity. Oh boy. This is a big one. So it's going to be 1 over 1 plus x minus 1 over 3 times 1 plus 2/3 x is equal to x plus 2 over 2x squared plus 5x plus 3. Okay? So this is going to be making these two both common denominators and then solving from there. So this, I don't like this fraction, and we can expand it. So this is actually equal to 3 plus 2x. So I'll change that here. So this is equal to 3 plus 2x. And then we can simply make them the same denominator, which is 3 plus 2x plus 1 plus x over 1 plus x times 3 plus 2x. Okay, and then this is, of course, equal to 4 plus 3x over, and then we can simply expand this. Oh, sorry, it's minus. So this should be minus 1 minus x, my bad. Sorry, minus 1 minus x. So this is not equal to 4 plus 3x, but it's in fact equal to x minus 2. It's x plus 2. And if we expand this, which we'll quickly do, is 2x squared, x plus 3, 3x, 2x plus 1, 5x, and then 1 times 3. 3, as you can see, we've got the same answer as the top. But there is a second part to this problem. And that second part is that we need to use the binomial expansion to find the first 4 terms of the expansion. Oh no. First 4 terms of the expansion of this. And what we need to do is we actually need to expand these 2 terms to get the expansion of this over here. So let's expand them over here. Find the first 4 terms, and we are expanding 1 plus x to the negative 1 plus minus 3, 1 over 3 plus 2x to the negative 1. Okay. Minus 1, no, it's 3 plus 2x. 3 plus 2x to the negative 1. So let's expand this. Okay. So 1 plus x to the negative 1 is going to be 1 minus x plus x squared minus x to x cubed. Pretty simple expansion. We've covered it in a previous video. And we need to subtract the expansion of this. So actually we need first, before expanding this, we need to transform it into the form 1 minus something or 1 plus something. And we'll do that by dividing everything by 3. So 3 times 1 plus 2/3 x to the negative 1. And we can simply expand this now. Oh, sorry. So this would be 1/3 times 1 minus 2/3 x plus 4/9 x squared minus 8 over 27 x cubed. Okay, pretty simple. And so if we divide everything by 1/3, this is equal to 1/3 minus 1/3 plus 2 over 9, because remember this is minus 4 over 27 plus 8 over 81 x cubed. Oh, I forgot all the x's. So now let's subtract the 2. So 1 minus 1/3 is equal to 2/3. 2 over 9x minus x is equal to 7 over 9x. X squared minus 4 over 27 is equal to 23 over 27 x squared. And finally, 8 minus x is equal to 81 minus 8 is equal to 73. Yeah, 73 over 81 x cubed. So that should be our final answer, and I think this is it. But let's just check. Yeah, so we've got that correct. So let's move on to the next problem. So the next problem is that we need to show that, I'll write it out. We need to show that n choose 0 plus 3 times n choose 1, n choose 1 plus 3 squared times n choose 2 is equal to 2 to the power of 2n. Okay, this is pretty simple. This is a binomial expansion again. So if you remember, the 1 plus x to the n binomial expansion is equal to n choose 0 plus n choose 1 x plus n choose 2 x squared. And so on. Yeah, and so from this, since it's more or less substituting 3 into x's position, we know that x is equal to 3, and so we can substitute that in here. So we get that 1 plus 3 to the n, this entire sequence is equal to 1 plus 3 to the n, which is equal to the 4 to the n. But if we do some rearranging, that's equal to 2 squared to the n, which is equal to 2 to the 2n. So we've successfully proved it. Over there. Okay. Pretty cool. Okay, let's move on to the next one. So now we need to prove by contradiction that if x equals 3, then 5x minus 7 is not equal to 13. This one looks pretty simple. We substitute x equals 3. Say that, okay, we say that 5x plus 7, sorry, because okay, so say we have our two statements, 5x minus 7 is equal to 13, and we substitute 3 here. Say x equals 3, that's 5 times 3 minus 7 is equal to 13. 15 minus 7 is equal to 13. So it gives us 8 is equal to 13. Since this statement is definitely false, then this original statement is definitely false. Like it must, then this original statement must be true because they are not equal, thereby proving it. So that was a pretty fast one. Next, we have the problem prove by mathematical induction that okay, this one looks pretty hard, so I'll write it out. We have 1 times 1 factorial times 2 factorial and so on until, n to the n times n, 2 squared times 2 factorial. Okay, so it's 1 to the 1 times 1 factorial, 2 to the 2. N to the n times n factorial is equal to n factorial n plus 1. So, if you remember proof by induction, we need to prove that the base case first is true. In this case, our base case is when n is equal to 1. So we need to prove that 1 to the 1 times 1 factorial is equal to 1 factorial to the power of 1 plus 1 factorial. In this case, we have 1 is equal to 1, so we have proved our base case to be true. So now we need to do the inductive step. So we need to prove that, so we have 1 to the 1 times 1 factorial times 2 squared times 2 factorial. Okay, so if we do all of that until n to the n times n factorial, we need to prove that it is true for the n plus 1 case, assuming that this is true. So what we can say is that we need to multiply n plus 1 to the n plus 1 power times n plus 1 factorial, and this should be equal to, and if we substitute n plus 1 here, n factorial to the n plus, okay. So it should be equal to n plus 1 factorial to the power of n plus 2. Okay, let's work around proving this. So we know that, let me zoom out. We know that since we're assuming that this holds true for some n, we know that that's equal to simply n factorial to the power times n to the power of n plus 1. Okay? And so we need to simply prove the equality of all of this. So, what to do? Okay, so the thing is, we can split this up into n plus 1 to the power of n plus 1 times n plus 1 factorial, of course. And the thing is that we can actually add these two together. Let me show you how. Because they're of the same power, it's the same as saying it's n factorial times n plus 1 all to the power of n plus 1 And since this is the case, and we know that n factorial times n plus 1 is actually equal to n plus 1 factorial. So that's true to the n plus 1. And since we're multiplying it by another n plus 1 factorial, that means the result is simply equal to n plus 2 factorial, which is what we needed it to prove. So that was pretty good. Since we've proved the inductive step and we've also proved the basic step that it holds true for when n equals 1, through the process of mathematical induction, we've proved that this statement is true. Okay, let's move on to the next problem. So the next problem is that use mathematical induction to prove the following statement. And I'm only going to do one of them again because I'm trying to, sorry, to plug in my laptop, but I am trying to speedrun this, and I'm going to leave the easier one for you to do, and I'm going to take the harder one for myself. So the harder one is from r is equal to 1 to n. We need to prove r squared is equal to, the sum of r squared is equal to n times n plus 1 times 2n plus 1 divided by 6. Right, this is the sum of squares, so we need to prove it. Okay, basic step, we need to prove 1 squared is equal to 1 times 1 plus 1 times 2 times 1, which is 2 plus 1, divided by 6. And this is equal to 1 is equal to 6 over 6, which we know is true. So we've proved the basic step. Now we need to prove the inductive step. So how we do that is we need to say, okay, for some sum of r equals 1 to n plus 1 this time, assuming that the base case is true, we need to prove that that is equal to n times n plus 1 times 2n plus 1. So actually n plus 1 times n plus 2 times 2 times n plus 1, which is 2n plus 2 plus 1, which is 2n plus 3, divided by 6. Okay. So let's get around to proving this. So we know that this is actually equal to, from r is 1 until n, r squared plus n plus 1 squared. It's just like that. Since we know that if it's the sum of r plus 1 to n, and we add whatever term n plus 1 happens to be, then we should get the same answer. And we know this is equal to this previous statement, since we're assuming that it's true. So we have n times n plus 1 times 2n plus 1 over 6. N plus 1 squared should be equal to this sum up here. Okay, and so what we need to do now is add this to that fraction. So what we have is we have n times n plus 1, or actually it's better probably to word this as n plus 1 times n times 2n plus 1 plus 6 times n plus 1 squared divided by 6. And so that is equal to, if we combine like terms, we have n plus 1 times, well, it's n, let's expand this. So this would be n times 2n squared, plus n, plus 6 times n, plus 6, all over 6, of course. And so then we get n plus 1 times 2n squared plus 7n plus 6, which we know is equal to 2n squared 2n squared plus 7n plus 6 is equal to 2n plus 3n plus 1. No, n plus 2. 2n plus 3. So this would be equal to n plus 2 times 2n plus 3 times 2n plus 3 all over 6. Since we've proved that this inductive case, I mean, it should equal what we have up here, which it does, n plus 1, n plus 2, 2n plus 3, n plus 1, n plus 2, 2n plus 3. So we've proved the inductive step, and since we've proved that it works for the basic step, through mathematical induction, we've proved the statement to be correct. So, let's move on to the next one.
Hello. So, you might have noticed I jumped question 14, and that's because question 14 was very long, and at the very end, the mark scheme had an error in it. So, I am going to skip the question and maybe come back to it at a later point. So, what we're going to do instead is we're going to go straight to question 16. And question 16 is given that 2 plus x plus minus 7x squared over 1 minus 2x 1 plus minus x squared. Oh damn, this is really hard. They didn't teach you any of this. We didn't go through any of this, but okay, we'll go through it anyways. But that's okay, is equal to a over 1 minus 2x plus b over 1 minus x, 1 plus x, plus c over 1 minus x. Determine the values of a, b, and c. So that's step 1. And this is usually quite a hard problem, because what we have to do is we have to say, okay, 2 plus x plus minus 7x squared is equal to a times 1 plus x, well, times really 1 minus x squared, if we're multiplying everything by this denominator, plus b times 1 minus 2x times 1 minus x, which is 1 minus 3x plus 2x squared, and then plus c. And c is going to be 1 minus x minus 2x squared. Okay. And so, oh, I need to get another mouse. But anyways, so we know that 2 is equal to a. We have to solve a system of linear equations. 2 is equal to a plus b plus c. 1, or the coefficient of x, is equal to negative 3b minus c, and finally negative 7x squared, or negative 7, is equal to negative a plus b minus plus 2b minus 2c. So this is a trick called equating the coefficients, and we need to solve the system of linear equations in order to solve the problem. So from this equation, we get that c is equal to negative 3b minus 1. So we can substitute that into here, I guess. So negative 7 is equal to negative a minus plus 2b minus 2 times minus 3b minus 1, which is equal to negative a plus 2b plus 6b plus 2. And so from this equation, we get that a is equal to 8b plus 9, and we can substitute it back into this equation. Alright, sorry, I'm back again. Man, I'm being interrupted all day here. Okay, anyways, we know that A is equal to 8b plus 9, so we can substitute it into the top one. So we know 2 is equal to 8b plus 9 plus b minus 3b minus 1. And with our luck, we should get something that adds up. 8b plus b minus 3b is 6b, and that's equal to 2 minus 9 plus 1. 2 minus 9, 7. 2 minus 9, negative 7 plus 1, 6. Negative 6. So negative 6 is 6b, and b is equal to negative 1. A is 8b plus 9. That's 8 times negative 1 plus 9. That's equal to 1. And finally, C is equal to negative 3 times negative 1 minus 1, which is equal to 2. So we know that this is equal to, we erase these. We know that A was what? A is 1. So 1 over 1 minus 2x. B is negative 1. And C is 2. So the next part of this problem, I believe, is to find the first find some terms of this using the binomial expansion, and we would have to find the first. We would have to find the first 4 terms. Oh boy. So, this is going to be a long one. So, okay, found our mouse back. We need to find the first 4 terms. Let me just check we've got these fractions correct first before we progress. So we were at 16. Yep, we got those terms correct, so now let's move on. So we need to expand 1 minus 2x. Why does my mouse know about battery? 1 minus 2x to the negative 1 minus 1 plus x to the negative 1 plus 2 times 1 minus x to the negative 1. So just get the first 4 terms. 1 minus 2x quickly. 1 plus 2x plus 4x squared plus 8x, I believe. 8x cubed. And now we need to get this, so this would be minus 1 minus x plus x squared minus x cubed plus 2 times 1 minus x to the negative 1, which is simply 1 plus x squared plus x cubed. So if we add all of these terms up, we get 1 minus 1 plus 2, which is 2. 2x plus x plus 2x is plus 5x. 4x minus x squared plus 2x squared, which is equal to 5x squared. And 8x plus x plus 2x, which is equal to 11x cubed. And so that would be the first 4 terms of our binomial expansion. And let me just check, and that's correct. So we have solved question 16. Now it's time to move on to some harder questions quickly. Alright, I'm back, and so now we're going to be finishing off this test by answering a few of the exam style questions. So the first question we need to tackle is, Zoomin, is from a paper 1. It's the coefficient of x squared in the binomial expansion of 1 plus 3x to the n is where n is, I believe it's a real number, is a rational number, okay, is 495. Determine the possible values of n. Okay, so we have 1 plus 3x squared to the n, and we need to find the coefficient of x squared. Is there more than one value? Okay, let's see. So the coefficient of x squared should simply be 3x squared times n choose 2. So it should be n choose 2 times 3x squared. And so, if we square this, it would be n choose 2 times 9 is equal to 495. And so n choose 2 is equal to 495 divided by 9. 495 divided by 9 is 55. So we know that n factorial over 2 factorial n minus 2 factorial is equal to 55. Now we can straight away remove the 2 factorial from this, and we can simply say that, oh sorry, this should be outside the brackets, that it's n factorial over n minus 2 factorial is 55 times 2, which is 110. And so we know that n times n minus 1 must equal 110. Since we know n factorial is equal to n times n minus 1 times n minus 2 factorial. So n times n minus 1 is equal to 110, and we need to find all rational number pairs that satisfy this equation. So we can make this a quadratic. N squared minus n minus 110 is equal to 0. And assuming it is a rational number, let's plug it into the equation. Minus b, so 1 plus or minus the square root of 1 plus 4 times 110 times 1 divided by 2. And so what would this be? Well, this would be 1 plus or minus the square root of 4 times 110 is 440. So, okay, so we have 441. Okay, divided by 2. And so we should have 1 plus or minus 21 over 2. And because we need to remember that n choose 2, I think only works for positive numbers, I think the only solution to this problem is if we add these numbers together. So we get 22 over 2 is equal to 11. I think that's the only solution, but let me just check the mark scheme quickly. Oh no, apparently that you could have a negative number as the exponent. Okay, interesting, but that's fine. No, that makes sense. Okay. And so this could also be 1 minus 21, which is of course negative 20 over 2, which is equal to negative 10. So these are our two possible values for n. Pretty simple. Let's jump into the next one. So Quickly. So we have prove the binomial coefficient identity. This does not look like a fun problem. So the binomial coefficient identity means for any n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. This is the identity apparently. So I guess what we would do is write this out in permutations. N over k factorial n minus k factorial is equal to n minus 1 factorial over k factorial n minus 1 minus k factorial plus n minus 1 factorial over k minus 1 factorial times n minus k factorial. Okay, so let's see what we can do here. We want to make these two on the same denominator. And so for the denominator, let's use this, it's okay. Let's use this denominator we have on the right hand side. So if we write this in the form k n minus k, this means that we would so we would have to multiply n minus k to the top part over here times n minus 1 to make this k factorial n minus k factorial, since we multiplied the top and bottom by n minus k. Because note, n minus 1 minus k times n minus k is equal to n minus k factorial. Okay? And we need to add this to this, and to convert this, we need to multiply the top side by k. So that k minus 1 factorial becomes k factorial at the bottom. We're multiplying both top and bottom sides by k. So at this point, we can simply add the two. So, okay, and so that's a pretty neat solution. So we get that n minus k plus k times n minus 1 factorial is over k factorial n minus k factorial, and simply this is equal to n times n minus 1 factorial over k factorial n minus k factorial. And by this point, you should know that that's just equal to n factorial over k factorial times n minus k factorial. And so we proved it. It's a pretty neat direct proof. I think, yeah, they're the same. And so we've got that covered. On to the final few questions. So we need to prove by 22, prove by contradiction that for all positive integers, if n cubed plus 3 is odd, then n is even. Okay, so let's assume that for some n cubed plus 3 that is odd, then n is also odd. And so what we do here is we say n is equal to 2m plus 1, where 2m is an integer. And so let's cube this odd number, 2m plus 1 cubed plus 3. And so if we quickly expand this, we get, what is this, 8 m cubed plus 12m squared plus 6m plus 1 plus 3. And as you can see, there's a pretty obvious contradiction. So 1 plus 3 is 4, and since all of the other coefficients are even in this scenario, it means it's impossible for this n cubed plus 3 value to be an odd number, as it clearly is an even number. Oh, since we have contradiction, since if n is odd, then n cubed must be even. This proves by contradiction that for all positive numbers, if n cubed plus 3 is odd, then n is even. Okay. And we're on to our final question. Wow. Our final question is, oh dear. Find the first 4 terms in ascending powers of x of the binomial expansion of the third root of 1 minus x. Of course, x being less than 1. So this is simply 1 minus x. 1 minus x to the 1/3, and I'm not sure if we've ever done fractional exponents in binomials, but they work exactly the same as in the general binomial formula. And so the first, how many terms? 4 terms would be 1 plus 1 minus 1/3 x plus, and then this is where it gets tricky because we have to go 1/3 and then 1/3 minus 1, which is negative 2/3, over 2 factorial times negative x squared. And I'll write the 4th term for us, which would be 1/3 times negative 2/3 times negative 5/3, since it's negative 2/3 minus 1, or 1/3 minus 2, over 3 factorial times x cubed times negative x cubed. So this would be simply minus 1 over 9 x squared, and this would be minus 5 over 81 x cubed. So those are the first 3 terms: 1 minus 1/3, minus 1/9, and minus 5 over 81 x cubed. So let me just check that. Yep, we got that correct. So we'll move on to the second part of this problem. And the second and final part is use your answer to find an approximation for the cube root of 63 to 6 decimal places. Are you serious? Okay, so cube root of 63, 1 minus x to the cube root. So in this, this is out of bounds. X is less than or equal to 1. Oh, okay, no, I understand how to do it. So we need to be a bit sneaky here. We need to actually substitute x as 1 over 64, so that we get the expansion of 1 minus 1 over 64 cube, which is equal to 63, cube root 63 over 64, or cube root 63 over 4, and then we'll multiply the answer by 4. This is going to be cancerous. So anyways, 1 minus 1/3 times 1 over 64 minus 1/9 times 1 over 64 squared minus 5 over 81 times 1 over 64 cubed. And if you really want to die, you can do this without a calculator, but for me, I'm going to use a calculator. So this is, in my calculator, this is 1 minus 1 over 3 over 64, which is equal to 0.0052. Hold on.
Okay, I'm back. I'm really sorry about all that. I've got caught up. But we are back on the final question, and this should be all good. So once again, 1 minus 1/3 times 1 over 64 is 1 minus 0.0052. Oh, wait, 6 decimal places. So that would be 0.005208. 3. 0.083 minus 1 over 9 over 64 squared, which is a small number. It's 0.0000271 minus 5 over 81 over 64 to the cube, which is pretty much irrelevant at this point. It's like 0.0000002. So let's compute and note that we have to still multiply all of this by 4. Since remember, this is calculating for the cube root of 63 over 4. So we have to multiply all of this by 4, but let's calculate what this is first. So we have 1 minus 0.0052083 minus 0.0000271 minus 0.0000002. So I'm getting 0.99476644, and multiplying this by 4 gives us 3.970576, so we can round that to 8. And so that should be our, 3.979. That should be our final answer for tonight. This should be 7. So yeah, that is chapter 1 done of the IBHL math textbook. Well, time to start on the next chapter tomorrow. If you like this video, leave a like, and if you have any comments, if I should speed up or slow down, if I'm going too fast or if I'm going too slow, leave them down in the comments, and I'll see you tomorrow where we will begin on chapter 2. Bye-bye.